A data center manager powers a new high-density server rack, then caps it below plan because the cooling loop has reached its heat removal limit. The paid-for processors are present and powered, yet usable AI capacity stops at the cooling system. The chips have not failed, and the electrical connection is available. The missing complement is the ability to carry their heat away reliably. A processor produces usable service only while the facility can remove its heat. So an added chip has little operational value when cooling capacity is already full. That changes the question from how many chips a facility owns to how much supported computing work it can deliver for a defined customer service promise. Consider a constructed enterprise data hall, not a claim about a named operator or current rack design. The people and site are fictional. The hall was sized for older racks. Its electrical connection can power the new rack, but the cooling loop cannot carry away the planned heat load at the intended operating density. The manager can run the rack conservatively, add cooling capacity, redesign part of the hall, or postpone more server purchases. Each path changes capital exposure. The visible consequence is economic. Expensive processors remain underused because heat removal, not chips, is the scarce input. Its return remains unrealized. Cooling is therefore not background overhead. It is a productive input that turns installed hardware into reliable computing service. It carries part of production. Every computation draws electricity into information equipment, and much of that energy becomes heat at a particular place and moment. Inside that same physical building, cooling and environmental control equipment regulate temperature and humidity, so information equipment can operate within required conditions during every scheduled operating period. That supporting system has a capacity of its own. Once it is full, adding processors can increase installed capital faster than usable output for the planned service level. The first reframe is simple. Hardware capacity is an invitation. Cooling capacity decides whether the invitation becomes service. That distinction changes investment decisions. Economists call this a complement problem. One input gains value only when another necessary input is available alongside it. The inputs must work together. For the constructed rack, usable output is limited by the tighter side, processor capability, or the system that removes its heat. The smaller capacity governs output. This is why a faster chip does not automatically create proportional service capacity inside an existing building. The surrounding building still matters. The International Energy Agency describes cooling and environmental control as equipment that keeps data center information technology within operating conditions. That is its documented support role. The same IEA report says cooling's electricity share varies from about 7% in efficient hyperscale facilities to more than 30% in less efficient enterprise facilities. The comparison covers different facility types. That reported range is not a universal constant. Facility type, system design, operating practice, and local conditions all change the cooling burden. Local evidence supplies the burden. The LBNL report likewise models power and water use effectiveness as dependent on cooling systems, operations, climate, facility type, and other infrastructure choices. Those relationships remain model dependent. Water may matter in some designs, but it cannot be reduced to one universal amount for an AI answer. It remains a site-level question. Cooling also has an operating cost: pumps, fans, treatment, maintenance, monitoring, and the energy used to move heat. Those costs recur every operating day. It has a capital cost too. Higher density computing can require different distribution hardware, heat exchangers, space, and retrofit work. Physical integration becomes part of investment. Reliability adds another layer. A facility that promises continuous service may need backup cooling capacity, as well as ordinary heat removal. That reserve carries its own cost. Together, these requirements make cooling a tax on usable computation, capital, energy, maintenance, redundancy, and in some systems water exposure accompany each productive rack. Those burdens shape capacity economics. The tax is not a fixed fee per chip. It changes with density, design, climate, utilization, and the reliability promise attached to service. The relationship remains operationally variable. Air, liquid, evaporative, and other heat rejection approaches are categories of choices, not a universal ranking of winners. Each category fits different constraints. Each approach shifts trade-offs among capital, energy, water exposure, maintenance, space, climate, and rack density. None erases the full trade-off. A dense rack can make heat removal more concentrated. An older hall can make a retrofit more disruptive and expensive. Existing layouts raise transition costs. Electrical availability and cooling availability can diverge. A facility may have power for a rack while lacking the thermal path to use it fully. That difference guides investment choices. That creates a decision. Cap the rack now, spend on a retrofit, move the workload, or delay the next hardware purchase. Each option reallocates scarce capital. The practical rule is to price the whole supported service, not just the processor in its box. Supported output is the relevant unit. Who pays when cooling is scarce? The owner may fund a retrofit, customers may face capacity limits, or another workload may lose its preferred location. That allocation affects several parties. Who bears the risk? A rushed retrofit can disrupt operations, while a delayed retrofit can leave expensive computing equipment. Underused, both paths can remain costly. Who gains when the constraint is solved? The facility can use more of the hardware it already owns, but only if other complements remain available. Other complements may still bind. One plausible equilibrium bundles cooling into a higher service price. So customers buy dependable capacity rather than a chip's theoretical maximum. The service promise shapes the bundle. Another equilibrium sells hardware access cheaply, then exposes users to lower supported capacity or separate infrastructures. Support can become a separate charge. Competition, contracts, and ownership determine how much of this cooling burden appears in a price, and how much stays inside the operator's capital plan. Each structure distributes burden differently. The conclusion is not that cooling always dominates. In some facilities, processors, power, network access, or reliability can bind first. The binding input can move. The IEA range itself demonstrates variation across facilities. A cooling share near one setting does not dictate the burden in another. This is evidence of variation. The limitation is evidence-specific. A general range cannot determine the right retrofit system or capacity level for a particular site. Site evidence must supply that answer. Water concerns also remain conditional. They depend on the facility's cooling approach, operation, climate, and supporting infrastructure. Generalizations need careful boundaries. A validating case is the constructed high-density rack inside an older hall. Power is available, but heat removal blocks the planned workload. This illustrates the stated mechanism. A rational exception is a lower density workload in a hall with cooling headroom. There, another complement may become scarce first. Its economics are therefore different. Another alternative is a purpose-built facility whose design aligns rack density, cooling architecture, redundancy, and local operating conditions from the start. Upfront coordination changes the result. The corrected claim is conditional. Cooling limits usable compute when it is the binding complement, not whenever a facility owns advanced chips. To evaluate a compute expansion, start with the workload density and the heat it concentrates in the room. Then inspect the existing complements, cooling capacity, distribution equipment, heat rejection, maintenance access, and backup coverage. Next, ask which conditions change the answer: climate, operating pattern, rack design, facility type, and the reliability promise. Finally, trace the economics, capital for upgrades, operating inputs, service risk, and the value of hardware that would otherwise sit below plan. The full resolution is that cooling acts like a tax on usable computation, because every reliable rack needs complementary heat removal capacity. Faster processors may reduce some computing costs, yet they do not erase the capital, energy maintenance, reliability, and system design demands of cooling. This is why more chips can create less additional service than their purchase price suggests inside a constrained hall. The practical test is not whether a rack can draw power for a moment. It is whether the whole facility can support its planned service reliably. When cooling is the tightest complement, buying another processor before expanding heat removal can leave capital idle. For future compute projects, test the processor plan against the cooling design, operating conditions, reliability target, and local resource exposure. Treat water claims with the same discipline. Ask which system, which site, which climate, and which operating pattern the claim actually describes. The next constraint sits outside the data hall. Even a technically cooled facility still needs a dependable grid connection to draw power. Cooling makes a chip usable only in a system that can support it. The future is just incentives at scale. See you tomorrow.